Welcome back, and let's talk about multi-fidelity optimization. Or why can't we discard bad configurations early? Well, we can, and we will now learn how. We do know that full evaluations yield the most accurate signal, but they also require a lot of resources. In practice, we often do have access to very cheap approximations or intermediate results of our evaluation. And we can use this to identify promising regions and configurations very early on. Such approximations are, for example, via subsampling training data, partial training only for a few epochs, downscaled images or signals, or smaller models. The question that we're going to address here is how can we use this information to increase the efficiency of Bayesian optimization? A concrete motivating example here is this figure: validation loss lower is better over the number of epochs, and the same here over the number of the training set size. We can see that even after only training the model, so each line is training one neural network with the different hyperparameter settings, we can see that already after a few epochs, we have a pretty good idea which of the configurations perform well. We need more epochs to identify the best performing configuration, but we could discard all of this very early on, and we don't need to spend resources on evaluating these models. The same here, we can get a pretty good idea of our objective function with a very small data set size. So there is no need to evaluate all models on the large data set. Now the question is, how can we formalize this into an algorithm? So let's start with a more formal definition also of the setup. We refer to an approximation of the true objective function as CB of delta, where B is our budget that we're willing to spend to evaluate this configuration, which is between Bmin and Bmax. Additionally, we also assume that a lower budget also correlates with cheaper evaluation costs, for example, compute costs. The objective, or the optimization objective, is always to find a configuration that performs best on the maximum fidelity, on the highest fidelity. So we assume that the highest fidelity is the best approximation that we have to our true objective function. And the scientific question is now, how can we do resource allocation efficiently across configurations? So which configurations do we evaluate on low budgets? Which do we evaluate on higher budgets? And the corresponding methods that implement this are called multi-fidelity methods. So we refer to the different budgets as fidelities, and the optimization methods are then called multi-fidelity optimization methods. They typically rely on three structural observations that we have. We observe that the error shrinks smoothly, so as the fidelity budget increases. We have seen this in the learning curve, which went down smoothly with more epochs. This also means that the ranks are approximately consistent across fidelities. This allows us to discard bad configurations early because we assume if they are bad in the beginning, they are also bad on a high budget. Last but not least, I said this before, the highest fidelity is the most accurate approximation of the true objective function. And yes, of course, in practice, these assumptions are not necessarily satisfied, and our optimization algorithm must be robust against that. Successive halving is the most prominent multi-fidelity optimization method available. It's intuitively very simple. We explore configuration with low budget and exploit configurations with higher budget. The method is relatively simple. We sample n random configurations, our candidate configurations. We evaluate them on a budget. We would start with Bmin. We keep the top fraction of our candidates, so 1 over eta, and then we increase the budget by this same factor, and we repeat this until only one configuration is left or the maximum budget is reached. So this means the key parameter of this successive halving algorithm is this eta, which is larger than 1, and it controls how quickly we discard configuration and increase the budget. So if for eta is, for example, 2, of course, this is an error, a successive halving halves the configurations and doubles the budget. If we increase our eta, we do more aggressive pruning. And if we have a smaller eta, we have gentle pruning and more guarded exploitation. Of course, this also has some limitations or disadvantages. It's very sensitive to early decisions. So if our B-min is set to too low, we might discard good configurations that just require a bit more budget. For example, larger models require a few more epochs to perform well. And secondly, we don't have adaptive samples. Our configurations are sampled randomly so far, which means we do not learn anything so far. There is no Bayesian optimization involved. We don't build a surrogate model. And we will now discuss 2 extensions. One is addressing the first problem, the sensitivity to early decisions. This is called hyperband. And the second one is, I already teasered it, we do Bayesian optimization instead of random sampling. So hyperband it's also a very simple extension. We simply rerun successive halving multiple times with varying lowest budget. So the idea is, as I said, run successive halving with different resource allocation schedules. And the main idea is that in each bracket, so this is what we call one run then of successive halving, is we use the same total budget. And by that we trade off our eta and our B-min. For example, if we have a large eta, we want a small B-min, so we do a very broad exploration. We explore many configurations on the low budget and then aggressively prune. If we start with that higher minimal budget, we do less aggressive pruning. And the intuition here is that at least one configuration is close to the optimal allocation, and the method is robust against budget constraints. The second extension is getting model in there, combining this with Bayesian optimization. And the idea is we use past observations to bias the selection of new configurations. And of course, the surrogate model needs to know about at which fidelity level we are. So once there are enough or sufficient observations per fidelity or per budget, we can replace random sampling with Bayesian optimization. So in our pseudocode, so here, instead of sampling configurations, we don't sample them at random, we sample them from a model. And the intuition here is that we can even faster exploit promising regions. We can also look here at empirical results. So we have regret, which is lower is better over time. We can see random search as a baseline in black. We can see Bayesian optimization in red. And what we can immediately see then, as soon as we go to multi-fidelity methods, in this case here Bob and hyperband in yellow and green, they already achieve performance before Bayesian optimization has finished the first configuration. So Bayesian optimization always evaluates at the full budget. Whereas for hyperband and Bob, we can already evaluate configurations on lower budgets, which means we have a tremendous speed up with small budgets. And then as we continue, we can also see that the model kicks in. So here we have Bayesian optimization performing better than hyperband, so that the distance between yellow and green. Of course, there are all alternatives and extensions to the 2 methods or 3 methods that I just explained. Modern methods, they can further exploit parallelism on structure. So for hyperband, or also Bob depends on that you evaluate one bracket one after the other and then move on, and that you also evaluate all configurations on one budget and then move on to a higher budget. So it's a synchronous method. There are asynchronous extensions that remove this barrier. Secondly, there are learning curve methods that directly assume that we are handling learning curves here and extrapolate this from partial evaluations. So if we have only seen the few initial loss points of a learning curve, we can extrapolate how the learning curve will look like with more budget. And this can also be combined with scaling laws, where we exploit predictable trends as a function of compute or data to extrapolate even more reliably from small budgets. The conclusion and takeaways here are multi-fidelity methods improve the efficiency by allocating resources adaptively, by either doing successive halving, evaluating many configurations with small budgets, and then pruning or hedging over multiple resource allocation strategies such as hyperband, or combining this with Bayesian optimization and doing more adaptive resource allocation. Last but not least, the performance here depends on the quality of low fidelity signals. So when we run hyperparameter optimization, we need to think about, okay, what is the lowest budget where we can still get a reliable signal? And then how do we want to navigate in this in our budget space and do a good resource allocation strategy?